Atlantis Rising Research Group, audiobooks.
From the Atlantis Rising Research Group news blog. Colossal black holes dance at heart of galaxy. Astronomers find evidence for the tightest-knit supermassive black hole duo observed to date. By Whitney Clavin. Locked in an epic cosmic waltz, 9 billion light-years away, two supermassive black holes appear to be orbiting around each other every 2 years. The two giant bodies each have masses that are hundreds of millions of times larger than that of our Sun, and the objects are separated by a distance roughly 50 times that which separates our Sun and Pluto. When the pair merge in roughly 10,000 years, the titanic collision is expected to shake space and time itself, sending gravitational waves across the universe. A Caltech-led team of astronomers has discovered evidence for this scenario taking place within a fiercely energetic object known as a quasar. Quasars are active cores of galaxies, in which a supermassive black hole is siphoning material from a disk encircling it. In some quasars, the supermassive black hole creates a jet that shoots out at near the speed of light. The quasar observed in the new study, PKS 2131-021, belongs to a subclass of quasars called blazars, in which the jet is pointing toward the Earth. Astronomers already knew quasars could possess two orbiting supermassive black holes, but finding direct evidence for this has proved difficult. Reporting in the astrophysical journal Letters, the researchers argue that PKS 2131-021 is a very rare candidate for a pair of supermassive black holes caught in the act of merging. The first candidate pair, within a quasar called OJ287, orbit each other at greater distances, circling every 9 years versus the 2 years it takes for the PKS 2131-021 pair to complete an orbit. The telltale evidence came from radio observations of PKS 2131-021 that spanned 45 years. According to the study, the powerful jet emanating from one of the two black holes within PKS 2131-021 is shifting back and forth due to the pair's orbital motion. This causes periodic changes in the quasar's radio light brightness. 5 different observatories registered these oscillations, including Caltech's Owens Valley Radio Observatory, OVRO, the University of Michigan Radio Astronomy Observatory, UMRO, MIT's Haystack Observatory, the National Radio Astronomy Observatory, NRAO, Metsähovi Radio Observatory in Finland, and NASA's Wide Field Infrared Survey Explorer, WISE space satellite. The combination of the radio data yields a nearly perfect sinusoidal light curve unlike anything observed from quasars before. When we realized that the peaks and troughs of the light curve detected from recent times matched the peaks and troughs observed between 1975 and 1983, we knew something very special was going on, says Sandra O'Neill, lead author of the new study, and an undergraduate student at Caltech, who was mentored by Tony Reedhead Robinson Professor of Astronomy, Emeritus. Most, if not all, galaxies possess monstrous black holes at their cores, including our own Milky Way galaxy. When galaxies merge, their black holes sink to the middle of the newly formed galaxy and eventually join together to form an even more massive black hole. As the black holes spiral toward each other, they increasingly disturb the fabric of space and time, sending out gravitational waves, which were first predicted by Albert Einstein more than 100 years ago.